Moving on to second lecture in chapter 11. We're going to start predicting electronic geometries. So let's look at the electronic geometry, the geometry and bond angles of PCl3. So do the Lewis structure. So phosphorus is in the center with chlorines attached to it. Phosphorus has 5 valence and chlorine has 7, and this is counted over for the periodic table, so this is 26 electrons. So you have 6, each line is 2, so 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Okay, everything is accounted for, and this is 4 groups. So phosphorus, it has 4 groups, 3 bonding, 1 lone pair. This is then, this is a pyramid. So this is trigonal pyramidal. Trigonal pyramidal geometry. And the bond angles, they're going to be less than, so 109.5 is going to be greater than the angles. So it's going to be less than that 109.5 perfect geometry of the tetrahedron. So same thing for ICl4 minus. So ICl4 minus. So we have iodines in the center, and we're going to have 4 chlorines around that, and there's 7 electrons for each of the halogen, plus 1, 36 electrons. So 4 lines, 8 already placed, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. So iodine has 6 things. So 4 bonding, 2 lone pair. This means it's a square planar geometry, and the bond angles are all going to be 90 degrees with this. So those are the angles there of a square planar. Okay, and I'm using the chart that was used in the previous lecture just so you know what I mean. I mean this chart here. So this chart here, and I more or less have it memorized, but you do not have to have it memorized. You can have it as a reference. So let's predict the shape of a larger molecule. So methanol. So methanol, and it's already written CH3OH, COH. I mean, it's already written as the electronic structure, and that's what it is. So each interior atom, this is 4 things. It's a tetrahedral. I mean, if you look at the carbon atom here has a hydrogen, another hydrogen, another hydrogen, and an oxygen atom attached to it. Those are 4 things. Now, if you look at the oxygen atom has 2 things, or two bonding, 2 lone pairs. So tetrahedral here, and it's a bent structure here. And the bent structure, at least molecular geometry that way. So, and there's a sketch of the molecule. All right, let's see if you can follow. What is the shape of ammonia? And we've already covered it. It's pyramidal. And what about ozone? Ozone has got, ozone is going to be right here. It's bent. It's supposed to be an arrow. There we go. Looks like an arrow now. All right, so ozone is bent. Ammonia is pyramidal. Okay, so moving on, we're going to talk about bond polarity. So, or if a molecule is polar or not. We talked about hydrochloric acid last chapter and how it was like the blanket thief, and we have a partial positive, partial negative. So this molecule is in fact polar. So it's a polar molecule. The carbon dioxide, it's a linear molecule. So it's a linear molecule, just like hydrochloric acid is a linear molecule. But here, you have oxygen and carbon, and oxygen draws electron density. It's a polar bond, so it draws electron density away from the carbon. But there's another oxygen on the other side that draws electron density the other way. And as it's pulling on this, the two vectors would create a dipole moment cancel out. So hydrochloric acid, the entire molecule is polar, but carbon dioxide, since the vectors are pulling on each side, they cancel each other out. I'm showing here some vector addition. So if you have vector going up and down, they cancel left and right, and the same magnitude, they will cancel to zero. So in this case, since it's the same atom, it's pulling the same force, they cancel out, and carbon dioxide is not a polar molecule. Now, what about water? So water has, you see here in the blue, it's drawing electron density towards the hydrogen, towards the oxygen. And with this, I have the components written in red, and the smaller arrows, with this diagonal arrow, there's a component up and a component sideways. And the sideways components cancel each other out, but the component towards the oxygen going up, the oxygen atom, add, and then because of it, you end up having negative charge build up right there. So you have a negative charge build up along the head of the oxygen, or the head of the molecule, the oxygen in the molecule, and then the hydrogen ends are going to have a partial positive charge in there because the electron density is building up towards that way. And keep in mind, this is the proper way to do the Lewis structure, but realize that it's a projection, that those two hydrogens are actually sticking out at you. It's not like it's a planar molecule. Water's not a linear molecule, it's a bent molecule from that. So here's how to summarize shape and polarity. So determine if there's a polar bond. It's really easy to figure out if there's a polar bond. If there's different atoms, it's a polar bond. And then you have to look to see. Here are the general rules. So the general rules are all bent molecules and all pyramids, they're polar. They're always polar. Now with linear, planar, and tetrahedral, you have to look at it a little more closely. Okay, so linear molecule, if the atoms are different, it's polar. So like in yellow here, I have HCN. That's a polar molecule. The atoms are different. In carbon dioxide, they're the same. If they're the same, they're nonpolar. If they're different, they're polar. For planar, I have boron trifluoride and formaldehyde. So boron trifluoride, it's all the same atom. It's all the same fluorine. That is nonpolar. If there's one different, like you have here with formaldehyde, you have carbon bonded to hydrogen, and oxygen. Oxygen's different, therefore this is a polar molecule. You actually have a buildup of negative charge on the oxygen end of the molecule. Now for tetrahedral, if all the atoms are the same, it's nonpolar. If one or more are different, it's polar. So let me give you an example here. Methane, this is nonpolar. So let me get rid of. So let's say I'm going to put a chlorine here. Chlorine here, have chloromethane. This is polar. Let me add another chlorine right here. Methylene chloride. This is polar. Let me add another chlorine. Chloroform. This is polar. Let me add another chlorine for carbon tetrachloride. These are all the same. This is nonpolar. Okay, so see that all bent, all pyramids are polar. If it's linear, planar, or tetrahedral, if all the same atom, it's going to be nonpolar. If one or more atoms are different, it's polar. So, okay, and also if you want to go on, that's more or less we're going to cover in this semester. But if you can go on further for the octahedral, if one or more of the bond, well, with octahedral you have it just depends. You have to look at it piecemeal. across the lines. So if you have two groups that are opposite each other, then it could be nonpolar. But, well, we'll save that discussion for a different time. But if you want to learn more, I'd be happy to talk to you. And there's also higher amounts of VSEPR. We stop at octahedral, but there's more. You can study more if you'd like. So, okay. So moving on. Determine if ammonia is polar. So ammonia is a pyramidal structure, and all pyramids are polar. This ammonia is in fact polar because of that. Okay, so let's look at these. What do you think is the first one here? Is this polar or nonpolar? So I'll use pink. You have electron density flowing this way, and then you have electron density flowing this way. It turns out these two arrows cancel out, and this molecule here is nonpolar. Another hint about polar nonpolar. If a molecule is a hydrocarbon, it's going to be nonpolar. Now, in this example, we have a fluorine and we have a chlorine and similar opposite things. But the thing is, the fluorine has a higher electronegativity, so it's pulling more electron density there than the little tiny chlorine. And because of that, this molecule is polar because it's not even split. The vectors are different. And here you have vector here, vector here. They cancel out along there and they go this way, and then this molecule is in fact polar. We'll talk about this in the next lesson, but this symbolism, you have trans. Notice that this is across the double bond, and this way is cis. It's on the same side. So trans is opposite, cis is same. And so here's a chemistry joke for you. What is this? This is known as transparence. Ha ha ha. That's one thing about being a chemist. The humor is just this horrible. Okay, so with this, maybe you've heard of something called trans fatty acids. All fatty acids are cis, at least naturally. If you get things that are unsaturated, specifically if you have something triple bond and you hydrolyze it, how do you hydrolyze an oil? You add acid to it and it hydrolyzes. So you add acid to it, it hydrolyzes, and you get a double bond, and they form mixtures of both cis and trans, but all naturally occurring fatty acids are cis. So, and all the fats for all the plants and animals here on Earth exist as a triglyceride, where you have OH, and then you have the fatty acids attached to them, like so. And of course, you have hydrogens. You have hydrogens there, hydrogens there. So they're triglycerides. What they look like molecular-wise, they kind of look like this. It'll be kind of a sphere. Because you have the backbone, but the fatty acid groups will try and be as far away from each other as possible that way, and they'll be cis. They'll be kinked towards this. Trans, if it was a complete like a complete trans fatty acid, it'll look more like kind of like that, like a fan blade or something like that. There'll be straighter chains looking thing, but the real fatty acids, the real is in made not further hydrolyzed by humans, are going to look more like this. And we're not. This is just it's not. We're not used to dealing with this. Our body has to change the trans to cis, and it takes energy to do that. So it's a little harder on our bodies to take the trans fatty acids. So okay. And the last thing we'll talk about is the chemistry of soap. So soap is really, truly a magical substance, and people don't think about it that much. Let's say you're cooking something, like you got olive oil all over your hands, and Now you have olive oil on your hands. What do you get rid of it? You can wipe it off, right? You can take a towel and you wipe it off. You still have this little thin film of olive oil, and you can run water over it. You can run hot water. It thins it out a little bit, but no matter what you do, you're gonna have a little bit of a thin film of oil on it. Or you can just take soap and you can rub it together. Take your hands, rub them together, and the soap magically washes away all the oil. And why is it hard to get rid of oil? Oil is nonpolar, and water is polar. And things that are polar and nonpolar tend not to mix together. So I didn't cover this, but polar things mix with polar things, nonpolar things mix with nonpolar things. Nonpolar and polar tend not to mix together. So that's called the like dissolves like rule. It's not. A lot of people think that the oil hates the water. Actually, the oil loves the water. Water's got a charge on it. It's a polar molecule. The electron clouds surrounding an oil molecule is like, ooh, look at that positive charge in the back end of that water molecule. Let me take a closer look there. And the water's like, nope, and pushes it out of the way, and by gravity, then it floats to the top. So really, water is kind of a bully when it comes to oil. It'll kick it right out and hang out with its polar friends, and the non-polar are stuck to hang out on the surface. But so you can't dissolve it, right? If you have like if I ever make something and I get sugar, like I've tried to make caramel and usually fail, and I'm like, okay, how do I clean this caramel off the pan? I'll let it soak in water, and the water tends to dissolve all the caramel. It's really easy. Or rock, like if you make rock candy or something like that, and you get all this crystallized sugar, what do? You fill it up with, you dump out the solution, you fill it up with fresh water, and you wait a couple hours, and then it all dissolves. So solution or the dissolving stuff is an easy way to clean things, right? So, uh, but when you have oil, it does not dissolve in water. So what do? You use soap. And notice there's a couple things. You have to have a little bit of water. Like if you're ever trying to clean a pan, you can't just take soap and rub it on the pan. You have to add a little bit of water, and then you have to add mechanical action, right? So when you have your hands, you put the soap on your hands, put it under water, and you rub your hands together, and that forms you're doing something. You're rubbing together. What you're doing is you're forming something called a micelle. So what a soap molecule is, it's here. You have a polar end and a non-polar end. At least most soap. Most soap is a anionic surfactant. So that means that this end here is negative charged. There's also cationic surfactants. That means it's positively charged. Cationic tend to be very rough on you, and they use them a little bit. They're used as fabric softeners and detanglers in like shampoo and conditioner. Okay, HBO. Thank you, HBO, for letting me know about that. All right. Now let me get back to talking about this. The other types of surfactants. So we have anionic, which is the most common. Cationic. We have non-ionic that have no charge. They're not very effective. There's amphoteric, which can be positive or negative depending on the pH. Those tend to be more expensive. They put non-ionic and amphoteric in No More Tears products. And then there's ethoxylated, which you take other ones and react it with ethylene oxide to make it better. But most common is the anionic. And when you rub it, so I mentioned that you have to like rub things together to form something. What you're forming is a structure called a micelle. And a micelle is, so here's the polar end, here's the non-polar end. It forms a sphere. So a sphere of molecules. And you have the negative end up here, it's polar, and you have the oil in here. So it makes these little oil droplets surrounded by these negative heads. And this whole thing is called a micelle. Now this whole thing can go in a solution and washes away. So really, really, truly a magical substance. And soap was first discovered, we believe, by the ancient Egyptians. And one thing about soap is always antibacterial. Unless it's a natural soap, then it may not be. But soap made by the way that they made soap is you take ash, and you can, and we've done this for thousands of years. You take animal fat, and then you take ash. You you from like a campfire, you take ash and you mix it up and you make basically potassium carbonate solution, and you mix that with animal fat and you saponify the fat, and then you make potassium stearate from that, and that's what they used for soap. And that's, for instance, that's also what the settlers in the United States did when they couldn't buy soap from England. It was too expensive, so they just made their own using like leftover animal fat. They would save their animal fat, save the grease from their food, and then save the ashes from their fire, and they would make soap. You can make soap from that. So that's good old fashioned soap, and that's antibacterial. It's always antibacterial. It's always been antibacterial. There was a labeling law changed in around the 1990s that said that in order for something to be antibacterial, it has to have an antibacterial agent, and the government listed the antibacterial agents, and you have to prove that it kills bacteria. But for a while, they put like triclosan was the antibacterial agent. They put it in everything in huge amounts, and then they realized that triclosan, although it's antibacterial, you don't have to put that much in there. So they say active ingredient triclosan, it's like 0.00001%, and like the rest is soap, and the soap kills everything anyway, so it's not a big deal. But okay, so we are done with this section for now, but we have more of Chapter 11. We have 4 videos in Chapter 11, so aren't you excited to watch all 4 of them? See you next time.